Please subscribe to support the channel. Our solar system began its remarkable journey approximately 4.6 billion years ago, not with a bang, but with a whisper of cosmic dust drifting through the vast emptiness of space. In a quiet corner of the Milky Way galaxy, a giant molecular cloud existed, composed primarily of hydrogen and helium, with traces of heavier elements forged in the hearts of ancient stars that had long since died. This cloud, stretching across light years of space, remained relatively stable for millions of years, a cold, dark nebula where temperatures hovered just a few degrees above absolute zero. Then something happened, perhaps the shock wave from a nearby supernova or the gravitational tug from a passing star, that disturbed this cosmic tranquility. The disturbance sent ripples through the cloud, creating regions of slightly higher density where gravity could begin its patient work. As these denser regions attracted more material, gravity's pull grew stronger, initiating a cascade effect that would transform this diffuse cloud into the structured system we know today. The solar nebula theory, our best explanation for this process, describes how the cloud began to collapse inward on itself, spinning faster as it contracted, much like an ice skater pulling in their arms to spin more rapidly. This rotation caused the cloud to flatten into a disk shape, with most of the mass concentrating at the center where pressures and temperatures began to climb dramatically. Over the course of several 100,000 years, the temperature at the core of this collapsing cloud reached millions of degrees, eventually triggering nuclear fusion reactions that marked the birth of our sun. Meanwhile, in the cooler outer regions of the spinning disk, dust grains began sticking together through electrostatic forces and gentle collisions, forming larger and larger clumps in a process called accretion. These growing aggregations, initially no larger than pebbles, continued to sweep up material from their orbital paths, some eventually reaching sizes of kilometers across, becoming planetesimals. The regions closer to the newborn sun, where temperatures remained high, saw the formation of rocky planetesimals, as volatile compounds like water, methane, and ammonia evaporated and were pushed outward by solar radiation. Beyond a certain distance, known as the frost line, temperatures were cold enough for these volatiles to condense into ice, allowing planetesimals in these outer regions to grow much larger by incorporating both rock and ice. The largest of these bodies, through their own gravitational influence, began to dominate their orbital neighborhoods, pulling in smaller objects and clearing paths through the debris-filled disk. This process of planetary formation took tens of millions of years, with countless collisions, near misses, and gravitational interactions, sculpting the architecture of worlds. Looking at our solar system today, one fact stands out with stunning clarity: the sun's absolute dominance over everything else in our cosmic neighborhood. When we calculate the mass of every planet, moon, asteroid, comet, and particle of dust within the sun's gravitational realm and compare it to our star itself, we discover that the sun contains 99.86% of all the mass in the entire solar system. This means that all 8 planets combined, along with their moons and rings, plus the asteroid belt, the Kuiper belt, and everything else account for less than 0.2% of the total mass. This staggering imbalance shapes the fundamental dynamics of our solar system, with the sun's gravity serving as the anchor that keeps everything else in orderly orbits. The sun itself is a massive sphere of plasma, approximately 1.4 million kilometers in diameter, large enough that over 1 million Earths could fit inside its volume. Its composition reflects the primordial makeup of the solar nebula, consisting of about 73% hydrogen and 25% helium by mass, with the remaining 2% comprising heavier elements like oxygen, carbon, nitrogen, and iron. Deep within the sun's core, where temperatures reach 15 million degrees Celsius and pressures are 250 billion times greater than at Earth's surface, hydrogen nuclei move with such energy that they overcome their natural electromagnetic repulsion and fuse together. This nuclear fusion process converts hydrogen into helium through a series of reactions known as the proton-proton chain. Every second, the sun converts approximately 600 million tons of hydrogen into 596 million tons of helium, with the missing 4 million tons transformed into pure energy, according to Einstein's famous equation. This energy, initially released as high-energy gamma rays, begins a long journey from the core outward, getting absorbed and re-emitted countless times by the dense plasma. The journey from the core to the surface takes photons anywhere from tens of thousands to millions of years as they random walk their way outward, gradually losing energy and shifting toward longer wavelengths. When these photons finally reach the surface and escape into space, they carry warmth and light across the solar system, providing the energy that drives weather patterns, ocean currents, and ultimately powers most life on Earth. The sun's energy also reaches the closest planet to its scorching embrace, Mercury, a small cratered world that experiences some of the most extreme temperature variations found anywhere in the solar system. Measuring just 4,879 kilometers in diameter, roughly 38% of Earth's size, Mercury orbits at an average distance of 58 million kilometers from the sun, though its highly elliptical orbit brings it as close as 46 million kilometers at perihelion and takes it out to 70 million kilometers at aphelion. This proximity to our star subjects Mercury's sun-facing side to intense solar radiation, heating the surface to a blistering 430 degrees Celsius, hot enough to melt lead, zinc, and tin, yet paradoxically, on the night side, temperatures plummet to minus 180 degrees Celsius, creating a temperature differential of 610 degrees, the largest of any planet in our solar system. This extreme swing exists because Mercury possesses virtually no atmosphere to distribute heat around the planet or retain warmth during its long nights. The planet's exosphere, a thin envelope of atoms knocked off the surface by solar wind and micrometeorite impacts, is so tenuous that it's essentially a vacuum, providing no insulating effect whatsoever. Mercury's slow rotation also contributes to these extremes, with one full rotation taking 58.6 Earth days, while its orbital period is just 88 Earth days, creating a unique 3-to-2 spin-orbit resonance, where Mercury rotates 3 times for every 2 orbits around the Sun. This relationship means that a solar day on Mercury, from one sunrise to the next, lasts 176 Earth days, giving the Sun ample time to bake one side before rotating to freeze the other. Despite its small size, Mercury possesses a surprisingly large iron core, making up about 61% of its volume compared to Earth's core, which accounts for only 17%. This unusually dense composition has led scientists to theorize that Mercury might have suffered a catastrophic collision early in its history that stripped away much of its rocky mantle, leaving behind a world that's mostly core, covered by a relatively thin rocky shell. Moving outward from Mercury, we encounter Venus, the second planet from the Sun, often called Earth's sister planet due to remarkable similarities in size, mass, and composition. Venus measures 12,104 kilometers in diameter compared to Earth's 12,742 kilometers, and its mass is roughly 81% of Earth's mass. However, any familial resemblance ends with these physical characteristics, as Venus has evolved into a hellish world that represents perhaps the most hostile environment for life anywhere in the inner solar system. The planet's surface temperature averages 467 degrees Celsius, even hotter than Mercury despite being almost twice as far from the Sun, and this temperature remains remarkably constant across the entire planet, from equator to poles, dayside to nightside. This uniformity and extreme heat result from Venus's thick atmosphere, which creates the most severe greenhouse effect known in our solar system. The atmosphere, 96.5% carbon dioxide with clouds of sulfuric acid droplets, creates a surface pressure 92 times greater than Earth's, equivalent to being almost 1 kilometer beneath Earth's oceans. This crushing blanket of gas traps incoming solar radiation with devastating efficiency. Sunlight penetrates the cloud layers and warms the surface, which then radiates heat in the infrared spectrum. But these longer wavelengths cannot escape back through the thick carbon dioxide, causing temperatures to rise continuously until reaching an equilibrium where the tiny amount of heat that does escape balances the incoming solar energy. The greenhouse effect is so powerful that Venus receives less sunlight than Earth due to its highly reflective clouds, yet maintains temperatures far higher than any other planet. The clouds themselves, concentrated in a layer from 45 to 70 kilometers above the surface, consist of sulfuric acid aerosols created by chemical reactions involving sulfur dioxide, water vapor, and sunlight. These clouds whip around the planet in just 4 Earth days, driven by super-rotating winds that reach speeds of up to 360 kilometers per hour, far faster than the planet's own rotation. Venus rotates so slowly that one Venusian day lasts 243 Earth days, longer than its orbital period of 225 Earth days, and it rotates in the opposite direction to most planets, meaning the sun rises in the west and sets in the east. Continuing our journey outward, we arrive at our own world, Earth, the third planet from the sun, and the only body in the entire universe where we know with certainty that life exists. What makes Earth so special isn't any single characteristic, but rather a precise combination of factors that together created and maintain conditions suitable for liquid water and biological complexity. Earth orbits at an average distance of 150 million kilometers from the Sun, placing it squarely within the habitable zone, sometimes called the Goldilocks zone, where temperatures allow water to exist in liquid form on the surface. Too much closer, and Earth would have suffered Venus's fate as a runaway greenhouse world. Too much farther, and it would be a frozen ice ball like Mars. But distance alone doesn't ensure habitability. Earth's atmosphere, composed of 78% nitrogen and 21% oxygen, with traces of other gases including carbon dioxide and water vapor, provides several critical functions. It creates a moderate greenhouse effect that raises average surface temperatures to a comfortable 15 degrees Celsius, compared to the -18 Earth would experience without atmospheric warming. The atmosphere also shields the surface from harmful ultraviolet radiation and burns up most meteoroids before they can strike the ground. Perhaps most importantly, Earth possesses a strong magnetic field generated by convection currents in its liquid iron outer core. This geodynamo creates a protective magnetosphere that extends tens of thousands of kilometers into space, deflecting most of the charged particles of the solar wind that would otherwise strip away our atmosphere, as happened to Mars billions of years ago. The magnetic field also prevents these particles from bombarding the surface with radiation that would be harmful to life. Earth's active geology, driven by heat from both its formation and the decay of radioactive elements within the planet, maintains plate tectonics that recycle carbon between the atmosphere and Earth's interior, helping to regulate climate over geological scales, through a negative feedback system. When Earth warms, weathering of rocks increases, pulling carbon dioxide from the atmosphere and eventually locking it in carbonate rocks on the ocean floor. When Earth cools, volcanic activity releases stored carbon dioxide back into the atmosphere, warming the planet again. This geological thermostat has helped maintain temperatures within a range suitable for liquid water for billions of years, despite the sun growing approximately 30% brighter over Earth's history. Earth's remarkable habitability has been shaped and maintained by an unlikely companion, our Moon, the fifth largest natural satellite in the solar system with a diameter of 3,474 kilometers, roughly 1/4 of Earth's diameter. The prevailing theory for the Moon's origin, supported by multiple lines of evidence including the composition of lunar rocks returned by Apollo astronauts, suggests that approximately 4.5 billion years ago, shortly after Earth's formation, a Mars-sized protoplanet called Theia collided with the young Earth in a glancing blow. The impact was catastrophic, destroying Theia and ejecting enormous amounts of material from both Theia and Earth's mantle into orbit. This debris, superheated to the point of vaporization, quickly coalesced in a ring around Earth and then aggregated to form the Moon within a matter of years to centuries, remarkably fast by geological standards. This violent birth explains several puzzling features of the Earth-Moon system, including why the Moon's composition closely matches Earth's mantle but lacks significant iron, which had already sunk to Earth's core before the impact. It also explains the system's unusually high angular momentum and the Moon's relatively large size compared to its parent planet. The Moon's influence on Earth extends far beyond its romantic presence in our night sky. Its gravitational pull creates tidal forces that raise bulges in Earth's oceans, and to a lesser extent in the solid Earth itself, as our planet rotates beneath these bulges. The friction between these moving tidal bulges and Earth's rotation acts as a brake, gradually slowing Earth's rotation and lengthening our days by approximately 2 milliseconds per century. In the distant past, days were significantly shorter, possibly lasting only 5 to 6 hours when the Moon first formed. As Earth's rotation slows, the angular momentum doesn't disappear, but transfers to the Moon's orbit, causing it to gradually spiral outward from Earth. Today, precise laser measurements bouncing off retroreflectors left on the lunar surface by Apollo astronauts show the Moon receding at a rate of 3.8 centimeters per year. Over the Moon's lifetime, it has moved from an initial distance of perhaps 20,000 kilometers to its current average distance of 384,000 kilometers. The Moon also stabilizes Earth's axial tilt, currently at 23.5 degrees, preventing dramatic variations that would cause extreme climate swings. Computer simulations suggest that without the Moon, Earth's tilt could vary chaotically from 0 to 85 degrees over millions of years, creating periods of extreme seasonal variation that might have prevented the evolution of complex life. Beyond Earth's orbit lies Mars, the fourth planet from the Sun, a world that has captured human imagination for centuries with its distinctive red appearance and tantalizing hints of past habitability. Mars appears red because its surface is rich in iron oxide minerals, essentially rust, created when iron in Martian rocks reacted with trace amounts of oxygen and water in the planet's past. The planet measures 6,792 kilometers in diameter, roughly half of Earth's size, with a mass just over 1/10 of Earth's. Mars orbits at an average distance of 228 million kilometers from the Sun, receiving less than half the sunlight that reaches Earth, contributing to its cold conditions where average temperatures hover around minus 63 degrees Celsius. The Martian atmosphere, 95% carbon dioxide, but incredibly thin at less than 1% of Earth's atmospheric pressure, provides minimal greenhouse warming or protection from radiation and meteorite impacts. Despite these harsh present-day conditions, overwhelming evidence suggests that ancient Mars was dramatically different, possessing a thicker atmosphere and abundant liquid water on its surface. Spacecraft orbiting Mars have photographed dried river valleys, ancient lake beds, minerals that only form in the presence of water, and sedimentary rock layers that speak to a time billions of years ago when water flowed across the Martian surface. The planet's northern lowlands may have once hosted an ocean covering approximately 1/3 of the planet's surface. What happened to this water remains one of planetary science's most intriguing questions. Some remains as ice mixed with soil, concentrated especially in polar ice caps that contain both water ice and frozen carbon dioxide. NASA's Mars Reconnaissance Orbiter discovered vast underground deposits of ice, and the Phoenix lander confirmed the presence of water ice just beneath the surface in the northern polar region. Much of Mars's water, however, was lost to space as the planet's magnetic field, generated early in Mars's history, shut down as the core cooled. Without this protective shield, solar wind gradually stripped away much of the atmosphere over hundreds of millions of years, and this atmospheric pressure dropped, liquid water became unstable, either evaporating into space or freezing into the ground. Mars hosts some of the solar system's most impressive geological features, including Olympus Mons, a shield volcano that towers 25 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest, with a base spanning 600 kilometers across, roughly the size of Arizona. This volcano and others in the Tharsis region grew to enormous sizes because Mars lacks plate tectonics, allowing volcanic hotspots to remain stationary and build upward for billions of years rather than creating chains of volcanoes as happens on Earth. Between Mars and Jupiter lies a region filled with millions of rocky and metallic objects ranging from dust particle size to nearly 1,000 kilometers across, collectively known as the asteroid belt. This belt occupies a vast donut-shaped region spanning from approximately 329 million kilometers to 478 million kilometers from the Sun. Though its total mass is surprisingly small, estimated at just 4% of the Moon's mass, or about 22 trillion kilograms. Despite its portrayal in science fiction, the asteroid belt is mostly empty space, with objects typically separated by millions of kilometers, meaning spacecraft can traverse it without encountering any asteroids unless specifically targeted. Early in the solar system's history, this region likely contained much more material, perhaps enough to form a substantial planet, but this never occurred due to Jupiter's gravitational influence. As the giant planet formed, its immense gravity stirred up objects in the asteroid belt region, increasing their orbital velocities and making collisions more violent and destructive rather than allowing gentle accretion into larger bodies. These gravitational perturbations also ejected many objects from the region entirely, scattering them throughout the inner solar system or sending them towards the Sun. The remaining objects continue to slowly grind down through occasional collisions, creating smaller fragments and producing a gradual rain of meteorites that fall to Earth and other planets. The asteroid belt's largest resident Ceres spans 939 kilometers in diameter and contains approximately one-third of the belt's total mass. In 2006, along with Pluto, Ceres received classification as a dwarf planet, a new category created to accommodate objects massive enough for their own gravity to pull them into a roughly spherical shape, but not massive enough to clear their orbital neighborhood of other debris. NASA's Dawn spacecraft, which orbited Ceres from 2015 to 2018, revealed a complex world with a rocky core possibly surrounded by a mantle of water ice, with a frozen crust marked by impact craters and mysterious bright spots that turned out to be deposits of sodium carbonate and other salts, remnants of briny water that had seeped up from below before evaporating. Some scientists speculate that Ceres might still harbor a subsurface ocean of liquid water, kept from freezing by a combination of salts acting as antifreeze and heat from radioactive decay in the rocky core. If confirmed, this would make Ceres another potentially habitable environment in our solar system, though any life there would face severe challenges surviving in such extreme conditions. Beyond the asteroid belt, we encounter Jupiter, the undisputed king of planets. A gas giant so massive that it contains 2.5 times the mass of all the other planets, moons, and asteroids combined. With a mass of approximately 1.9 times 10 to the 27th kilograms, Jupiter falls just short of being massive enough to trigger nuclear fusion and become a star, though it would need to be about 80 times more massive to sustain hydrogen fusion. The planet's equatorial diameter stretches 143,000 kilometers, 11 times larger than Earth, with a volume that can contain 1,000 Earths. Despite this enormous size, Jupiter consists primarily of the lightest elements, hydrogen and helium, giving it an average density only slightly greater than water. The planet lacks a solid surface, instead transitioning gradually from gaseous atmosphere to liquid hydrogen as depth and pressure increase. Deep within Jupiter, perhaps 15,000 to 25,000 kilometers below the cloud tops, pressures exceed 2 million Earth atmospheres, crushing hydrogen atoms so tightly that their electrons separate from their nuclei, creating a liquid metallic form of hydrogen that can conduct electricity. Convection current in this electrically conductive layer generates Jupiter's powerful magnetic field, 20,000 times stronger than Earth's, which creates a magnetosphere so large that if visible to the human eye, it would appear larger than the full moon from Earth's surface. Jupiter's role as the solar system's guardian cannot be overstated. Its immense gravitational field acts like a cosmic vacuum cleaner, capturing or deflecting comets and asteroids that might otherwise collide with inner planets. Computer simulations suggest that without Jupiter's protective influence, Earth might experience impact events tens or hundreds of times more frequently, potentially preventing the development of complex life. The most famous example of Jupiter's protective role occurred in July 1994, when comet Shoemaker-Levy 9, which had been captured by Jupiter's gravity and broken into fragments during a close approach, slammed into the giant planet in a series of spectacular impacts. Each fragment explosion released energy equivalent to millions of nuclear bombs, creating dark impact scars larger than Earth that remained visible for months. Jupiter's influence on the inner solar system extends beyond direct protection from impacts. During the solar system's formation, Jupiter's gravity may have prevented additional planets from forming in the asteroid belt region, and influenced the migration of other planets, sculpting the architecture we observe today. Some theories suggest Jupiter might have migrated inward toward the Sun early in solar system history, before being pulled back outward by Saturn's gravitational influence, a cosmic dance that would have scattered planetesimals and reshaped orbits throughout the young solar system. The swirling clouds visible in Jupiter's atmosphere create bands of alternating colors running parallel to the equator, with light-colored zones of rising gas alternating with darker belts of descending gas. These bands result from Jupiter's rapid rotation, the fastest of any planet, completing one revolution in less than 10 hours. This rotation, combined with heat rising from the planet's interior, creates powerful jet streams in the atmosphere, reaching speeds of up to 640 kilometers per hour. The atmospheric composition includes approximately 90% hydrogen and 10% helium, with traces of methane, ammonia, water vapor, and other compounds. The various colors in the clouds arise from complex chemistry involving these compounds, solar ultraviolet radiation, and charged particles from Jupiter's magnetosphere. Ammonia ice crystals tint zones white, while the darker belts contain compounds that have undergone chemical reactions, creating more complex organic molecules that appear brown or red. Embedded within this turbulent atmosphere, stable storm systems can persist for years or even centuries. The most famous of these, the Great Red Spot, represents a high-pressure storm system that has been observed continuously since the 1831, and possibly as far back as 1665, when astronomer Giovanni Cassini described a similar feature. This anticyclonic storm, currently measuring approximately 16,000 kilometers across, large enough to swallow Earth, has been shrinking in recent decades for reasons not fully understood. Wind speeds at the storm's edge reach 432 kilometers per hour, and the red coloration may result from complex organic compounds brought up from deeper in the atmosphere where they formed through chemical reactions. Jupiter's family of moons numbers at least 95 confirmed satellites as of the latest discoveries, though most are irregular captured asteroids just a few kilometers across. The four largest moons, discovered by Galileo Galilei in 1610, are worlds of remarkable diversity. Io, the innermost Galilean moon, is the most volcanically active body in the solar system, with hundreds of active volcanoes continuously resurfacing the moon and creating massive plumes of sulfur and sulfur dioxide that reach hundreds of kilometers into space. This extreme volcanism results from tidal heating, as Jupiter's gravity and resonant interactions with Europa and Ganymede constantly flex and squeeze Io's interior, generating enormous amounts of heat through friction. Europa, slightly smaller than Earth's moon, possesses a surface of water ice crisscrossed by cracks, ridges, and relatively few impact craters, suggesting a geologically young surface continually renewed by activity from below. Beneath this icy shell, perhaps 10 to 15 kilometers thick, evidence strongly suggests a global ocean of liquid water, perhaps 100 kilometers deep, kept liquid by tidal heating similar to that affecting Io, though less intense. This subsurface ocean, potentially containing twice as much water as all of Earth's oceans combined, represents one of the most promising locations in the solar system to search for extraterrestrial life. Where liquid water, chemical nutrients, and energy sources coexist, life as we know it becomes a possibility. And future missions hope to confirm Europa's ocean and perhaps sample it by landing on the surface and drilling through the ice, or analyzing material ejected into space by water vapor plumes that Hubble Space Telescope observations suggest sometimes erupt from the moon's south polar region. Ganymede holds the distinction of being the solar system's largest moon, even bigger than the planet Mercury, with a diameter of 5,268 kilometers. This moon possesses its own magnetic field, the only moon known to have one, suggesting the presence of a liquid iron core. Ganymede's surface divides into two distinct terrain types: dark, heavily cratered regions billions of years old, and lighter grooved terrain that appears to be younger areas where tectonic forces have resurfaced portions of the icy crust. Like Europa, Ganymede likely harbors a subsurface ocean, though buried beneath perhaps 150 kilometers of ice and rock layers, making it less accessible than Europa's ocean, but still scientifically fascinating. Callisto, the outermost Galilean moon, presents a heavily cratered surface that appears to have changed little since the solar system's early bombardment period, making it a time capsule, preserving information about the conditions in the outer solar system billions of years ago. Despite its ancient appearance, Callisto too may hide a subsurface ocean beneath its battered ice and rock exterior, kept liquid by the decay of radioactive elements within the moon rather than tidal heating. Moving outward past Jupiter, we encounter Saturn, the second largest planet in our solar system and arguably the most visually spectacular due to its magnificent ring system. Saturn measures 120,000 kilometers in diameter at its equator, 9 times Earth's diameter, and possesses a mass 95 times greater than Earth's, though this still makes it only 30% as massive as Jupiter. Like Jupiter, Saturn consists primarily of hydrogen and helium with no solid surface, instead transitioning from gas to liquid to exotic high-pressure phases as depth increases. Saturn's extremely low average density, just 70% that of water, means the planet would theoretically float if placed in an ocean large enough to hold it, though its rapid rotation, completing one turn in just over 10.5 hours, causes significant equatorial bulging that makes the planet noticeably wider at its equator than from pole to pole. Saturn's atmosphere displays banded cloud patterns similar to Jupiter's, though more subdued in color, with occasional storm systems including rare great white spots that appear every few decades, massive storms that encircle the planet before eventually fading. One such storm, observed by the Cassini spacecraft in 2010, grew to an enormous size, wrapping entirely around Saturn's equator and disturbing the atmosphere for months. However, Saturn's most famous and beloved features are undoubtedly its rings, first observed by Galileo in 1609, though his primitive telescope couldn't resolve them clearly, leading him to describe Saturn as having ears or handles. Not until 1655 did Christian Huygens correctly identify these features as a ring system encircling the planet. These rings, while appearing solid from a distance, actually consist of countless individual particles, ranging from dust grain size to house-sized chunks, each following its own orbit around Saturn. Spectroscopic analysis reveals that these particles are primarily water ice, appearing bright because ice reflects sunlight efficiently. The rings extend from approximately 74,000 to 140,000 kilometers from Saturn's center, spanning a distance wider than the gap between Earth and the Moon, yet remain remarkably thin, in most places just tens of meters thick. An observer standing on the rings would see them as a dense collection of icy boulders and pebbles separated by mostly empty space, similar to an extremely spread-out asteroid field. The ring structure reveals complex patterns including gaps, divisions, and thousands of ringlets, many sculpted by gravitational interactions with Saturn's numerous moons. Some small moons, called shepherd moons, orbit within or near the rings and use their gravity to confine ring particles to narrow bands, preventing the rings from spreading outward. The origin of Saturn's rings remains uncertain. Their bright, relatively pristine appearance suggests they may be surprisingly young, perhaps only 100 million years old, meaning dinosaurs roamed Earth when Saturn's rings formed. One theory suggests the rings resulted from the tidal disruption of a comet or small moon that wandered too close to Saturn, crossing the Roche limit, the distance within which tidal forces from the planet overcome the object's self-gravity, tearing it apart into countless fragments. Another possibility is that the rings represent remnants from the solar system's formation that never coalesced into a moon, though this seems less likely given their apparently young age. Recent data from the Cassini spacecraft, which deliberately plunged into Saturn's atmosphere in September 2017 to avoid contaminating potentially habitable moons, suggests that the rings may be losing material more rapidly than previously thought, raining particles down onto Saturn's atmosphere. If this mass loss continues at the observed rate, Saturn's rings might survive only another 100 million years, meaning we live in a cosmically rare time when this beautiful planet displays its magnificent crown. Saturn hosts at least 146 confirmed moons, more than any other planet, ranging from tiny moonlets just a few kilometers across embedded within the ring system to massive Titan, the second largest moon in the entire solar system. Titan, measuring 5,150 kilometers in diameter, larger than the planet Mercury, stands out as one of the most fascinating bodies in our entire solar system. It possesses a thick atmosphere, denser than Earth's, composed primarily of nitrogen with a few percent methane and traces of other organic compounds. This atmosphere, combined with Titan's relatively large size, means in many ways Titan resembles a planet more than a typical moon. Surface pressure on Titan reaches 1.5 times Earth's sea level pressure, and the thick, hazy atmosphere completely obscures the surface in visible light, requiring radar and infrared instruments to see through to the ground. When spacecraft finally penetrated this veil, they revealed a surprisingly Earth-like landscape featuring rivers, lakes, seas, clouds, rain, and familiar-looking erosional features, all composed not of water, but of liquid hydrocarbons, primarily methane and ethane. Titan represents the only body in the solar system besides Earth with stable liquid on its surface, though the liquid is natural gas rather than water, and surface temperatures of minus 179 degrees Celsius keep water frozen rock hard while allowing methane to exist in liquid form. Titan's methane cycle mirrors Earth's water cycle, with liquid hydrocarbons evaporating from surface lakes, forming clouds, falling as rain, flowing through river channels, and collecting again in seas and lakes. The largest of these bodies of liquid, Kraken Mare, in Titan's North Polar region, covers approximately 400,000 square kilometers, larger than the Caspian Sea on Earth, with depths possibly reaching hundreds of meters. The European Space Agency's Huygens probe, which landed on Titan's surface in January 2005, transmitted the first pictures from this alien world, showing rounded cobbles likely made of water ice, carved and shaped by flowing methane over geological time. Titan's surface also displays sand dunes near the equator, mountains, cryovolcanoes that may erupt ammonia water slush rather than molten rock, and vast plains of water ice mixed with organic compounds. The thick atmosphere and presence of organic molecules make Titan remarkably similar to early Earth before life began, though far colder, leading scientists to regard it as a natural laboratory for studying prebiotic chemistry and potentially an environment where exotic life forms adapted to liquid hydrocarbons might exist. Continuing outward through the outer solar system, we arrive at Uranus, the seventh planet from the Sun and the first discovered in modern times. Found by William Herschel in 1781, though earlier observers had noted it but mistaken it for a star. Uranus measures 51,118 kilometers in diameter, 4 times Earth's size, and possesses 14 times Earth's mass. The planet orbits approximately 2.9 billion kilometers from the Sun, taking 84 Earth years to complete one circuit, meaning Uranus has completed only one full circuit around the Sun since its discovery in 1846. The planet's discovery represents a triumph of mathematical astronomy, as astronomers predicted Uranus's existence and location by observing perturbations in Uranus's orbit caused by the gravitational pull of an unknown planet. When telescopes turned to the predicted location, they found Neptune within 1 degree of the calculated position. Neptune closely resembles Uranus in size and composition, measuring 49,528 kilometers in diameter, slightly smaller than Uranus, but actually more massive due to higher density. Like Uranus, Neptune's composition consists primarily of water, methane, and ammonia ices in their interiors rather than being primarily hydrogen and helium. Neptune's most distinctive characteristic is its extreme axial tilt of 98 degrees, meaning the planet essentially rolls along its orbital path on its side rather than spinning upright like most planets. This unusual orientation causes the planet's poles to experience 42 years of continuous sunlight, followed by 42 years of total darkness as Uranus orbits the Sun. During solstice periods, one pole points almost directly at the Sun, while the opposite pole faces deep space. This bizarre orientation has profound effects on Uranus's weather patterns and heat distribution, with some regions receiving no sunlight for decades, while others experience continuous day. The cause of this extreme tilt remains uncertain, though the most widely accepted theory suggests that Uranus suffered at least one, possibly multiple, collisions with Earth-sized or larger protoplanets during the solar system's chaotic early period. Such impacts would have been violent enough to knock the planet onto its side while not destroying it entirely. Computer simulations suggest that if such a collision occurred early enough when Uranus still had a surrounding disk of gas and debris, this material could have reformed into a new disk aligned with the planet's new equator, explaining why Uranus's moons orbit around its tilted equator rather than remaining in the planet's original orbital plane. Uranus's atmosphere, like other giant planets, consists primarily of hydrogen and helium, but contains a higher percentage of methane than Jupiter or Saturn. This methane absorbs red light while reflecting blue and green wavelengths, giving Uranus its distinctive cyan appearance. The planet's upper atmosphere remains remarkably calm compared to the violent storms seen on Jupiter and Saturn, with Voyager 2's flyby in 1986 revealing an almost featureless blue-green sphere. However, more recent observations as Uranus approached equinox have detected increased atmospheric activity, including clouds, storms, and atmospheric features that suggest the planet's weather patterns change significantly as solar heating shifts from one pole to the other. Beyond Uranus lies Neptune, the eighth planet from the Sun and the most distant of the traditional planets since Pluto's reclassification. Neptune orbits at an average distance of 4.5 billion kilometers from the Sun, taking 165 Earth years to complete one single orbit, meaning Neptune has completed only one full circuit around the Sun since its discovery in 1846. The planet's discovery represents a triumph of mathematical astronomy, as astronomers predicted Neptune's existence and location by observing perturbations in Uranus's orbit caused by the gravitational pull of an unknown planet. When telescopes turned to the predicted location, they found Neptune within 1 degree of the calculated position. Neptune closely resembles Uranus in size and composition, measuring 49,528 kilometers in diameter, slightly smaller than Uranus, but actually more massive due to higher density. Like Uranus, Neptune's composition consists primarily of water, methane, and ammonia ices in their interiors, rather than being primarily hydrogen and helium. However, unlike its nearly featureless neighbor, Neptune displays remarkably active weather despite receiving 900 times less solar energy than Earth and 40 times less than Jupiter. Neptune holds the record for the strongest sustained winds measured on any planet in the solar system, with jet streams reaching speeds up to 2,100 kilometers per hour, over 5 times faster than the strongest winds on Earth. These supersonic winds drive massive storm systems, including the Great Dark Spot observed by Voyager 2 in 1989, an anticyclonic storm system comparable in size to Earth. Curiously, when the Hubble Space Telescope looked for this storm system in 1994, it had vanished, only to be replaced by a different dark spot in the northern hemisphere. This suggests Neptune's major storm systems are transient features that form and dissipate over periods of a few years, unlike Jupiter's Great Red Spot, which has persisted for centuries. The source of energy driving Neptune's vigorous atmospheric activity remains puzzling, since the planet receives so little sunlight at its vast distance from the Sun. Scientists believe Neptune must possess a significant internal heat source, radiating about 2.6 times more energy into space than it receives from the Sun. This internal heat, likely a combination of primordial heat from the planet's formation and heat generated by gravitational contraction as heavier materials slowly sink toward the core, drive powerful convection currents that manifest as the violent storms and winds observed in the atmosphere. Neptune's striking deep blue color, More vivid than Uranus despite similar atmospheric composition, results from methane absorption of red light, though the exact reason Neptune appears darker and more intensely blue remains somewhat mysterious, possibly involving an unknown atmospheric component that enhances the coloration. Neptune possesses 16 known moons, dominated by Triton, the seventh largest moon in the solar system with a diameter of 2,700 kilometers. Triton stands out as one of the most unusual moons, orbiting Neptune in a retrograde direction, opposite to the planet's rotation and opposite to the direction of all major moons of the other giant planets. This backward orbit strongly suggests Triton did not form alongside Neptune, but was instead captured from the Kuiper Belt, a region of icy bodies beyond Neptune's orbit. When Triton was captured, likely through a gravitational interaction that reduced its orbital velocity enough for Neptune's gravity to trap it, the moon would have been on a highly elliptical and inclined orbit. Over hundreds of millions of years, tidal interactions with Neptune gradually circularized Triton's orbit, though this process generated enormous amounts of tidal heating within the moon. This heating may have completely melted Triton's interior, allowing heavier materials to sink to the center and lighter materials to rise, creating the differentiated structure observed today. Even now, billions of years after capture, Triton's retrograde orbit continues to decay, bringing it closer to Neptune. In perhaps 3.6 billion years, Triton will cross Neptune's Roche limit and be torn apart by tidal forces, potentially creating a magnificent ring system around Neptune that could rival or exceed Saturn's rings in extent. Despite its frigid surface temperature of -235 degrees Celsius, making it one of the coldest measured surfaces in the solar system, Triton displays remarkable geological activity. Voyager 2's flyby in 1989 revealed a young surface with relatively few impact craters, suggesting recent resurfacing through geological processes. Most surprisingly, the spacecraft observed active geyser-like plumes erupting from Triton's surface, shooting dark material up to 8 kilometers high before being caught by winds and deposited downwind as dark streaks. These eruptions likely result from seasonal heating by the weak but persistent sunlight that penetrates Triton's transparent nitrogen ice surface layer, warming darker material below until nitrogen ice vaporizes explosively. Triton's surface displays diverse terrain, including the frozen nitrogen ice cap at the South Pole, cantaloupe terrain consisting of dimpled and pitted areas unlike any surface seen elsewhere, and cryovolcanic flows where water-ammonia mixtures erupted onto the surface and froze. The moon's thin atmosphere, just 14 microbars of pressure, consists primarily of nitrogen, with traces of methane. And like Mars's atmosphere, it may freeze onto the surface during winter, then sublimate back into gas during summer. Beyond Neptune's orbit, we enter a vast region of space known as the Kuiper Belt, extending roughly from Neptune's orbit at 30 astronomical units from the Sun, where 1 astronomical unit equals the average Earth-Sun distance of 150 million kilometers, out to approximately 50 astronomical units. This region hosts countless icy bodies, remnants from the solar system's formation that never accumulated into planets due to the low density of material at such great distances from the Sun. The Kuiper Belt population includes hundreds of thousands of objects larger than 100 kilometers in diameter and possibly billions of smaller bodies, making it a far more massive and densely populated region than the main asteroid belt between Mars and Jupiter. These Kuiper Belt objects, or KBOs, consist primarily of frozen volatiles including water, methane, ammonia, and other ices mixed with rocky material, essentially making them frozen reservoirs of the pristine material that formed the outer solar system. The region's most famous former resident, Pluto, once classified as the solar system's 9th planet for 76 years after its discovery in 1930, was reclassified as a dwarf planet in 2006, when the International Astronomical Union established formal definitions for planetary categories. This controversial decision arose because astronomical surveys had discovered numerous objects in the Kuiper Belt comparable in size to Pluto,
including Eris, which is actually more massive than Pluto, though slightly smaller in diameter. If Pluto remained classified as a planet, logical consistency would require granting planetary status to dozens or potentially hundreds of similar objects, making the concept of a planet increasingly meaningless. Instead, the IAU defined planets as objects that orbit the Sun, are massive enough for their own gravity to pull them into hydrostatic equilibrium, creating a roughly spherical shape, and have cleared their orbital neighborhood of other debris. Pluto satisfies the first two criteria, but fails the third, as it shares the Kuiper Belt region with thousands of other objects. This reclassification sparked considerable debate and emotional response from those who grew up learning about 9 planets. Though scientifically, it represents a necessary refinement as our understanding of the solar system evolved. Pluto itself remains a fascinating world regardless of its classification. Measuring 2,377 kilometers in diameter, smaller than Earth's moon, but possessing 5 known moons of its own, the largest being Charon at 1,212 kilometers across, over half of Pluto's diameter. The Pluto-Charon system is so closely matched in size that they're sometimes considered a binary dwarf planet system, orbiting around a common center of mass that lies in the space between them rather than inside Pluto. The two bodies are tidally locked to each other, meaning the same hemisphere of each always faces the other, and they orbit this common center every 6.4 days. NASA's New Horizons spacecraft, which flew through the Pluto system in July 2015 after a 9.5-year journey, revolutionized our understanding of this distant world. Rather than the dead, cratered ice ball many expected, New Horizons revealed a geologically active world with diverse terrain including towering mountains of water ice rising 3,500 meters above the surrounding plains, glaciers of nitrogen ice flowing like terrestrial glaciers, though the ice is nitrogen rather than water, and vast plains younger than 100 million years old showing no impact craters whatsoever, suggesting recent geological activity. The most iconic feature, informally named Tombaugh Regio in honor of Pluto's discoverer Clyde Tombaugh, appears as a bright heart-shaped region about 1,600 kilometers across. The western lobe of this heart, Sputnik Planitia, consists of a deep basin filled with nitrogen ice that appears to be convecting in cells hundreds of kilometers across, with warmer ice slowly rising in the centers and cooler ice sinking at the edges in a process driven by heat from Pluto's interior. Pluto's surface displays a surprising variety of colors, from bright white nitrogen and methane ice to dark reddish-brown areas where methane in the atmosphere undergoes chemical reactions triggered by ultraviolet sunlight, creating complex organic molecules called tholins that settle onto the surface. The dwarf planet possesses a thin atmosphere of nitrogen with traces of methane and carbon monoxide that extends surprisingly far into space, blown outward by the planet's weak gravity and forming a long tail downstream from the solar wind. This atmosphere, which may partially freeze and collapse onto the surface when Pluto reaches the most distant point in its elliptical orbit, undergoes seasonal changes as the dwarf planet's 248-year orbit carries it from about 30 astronomical units to nearly 50 astronomical units from the Sun. The New Horizons mission also revealed details about Pluto's 4 smaller moons, Styx, Nix, Kerberos, and Hydra, which are much smaller and irregularly shaped, likely formed from debris ejected during the giant impact that created the Pluto-Charon binary system early in solar system history. Scattered throughout the inner solar system and occasionally visiting from the outer reaches, comets represent some of the most spectacular and historically significant objects in our solar system. These icy bodies, often described as dirty snowballs, consist of frozen water, carbon dioxide, methane, and ammonia mixed with dust and rocky particles, essentially frozen remnants from the solar system's formation, preserved in the deep freeze of the outer solar system. Comets spend most of their existence in frigid orbits far from the Sun, where they remain inactive, indistinguishable from asteroids except in composition. However, when a comet's orbit brings it into the inner solar system, solar radiation begins warming the frozen nucleus,
causing volatile materials to sublimate directly from ice to gas without passing through a liquid phase. This process begins beyond Mars's orbit and intensifies as the comet approaches the Sun, with escaping gases carrying dust particles along and forming an enormous cloud called a coma that can grow larger than Jupiter despite the solid nucleus being just a few kilometers across. The solar wind, a constant stream of charged particles flowing outward from the Sun, pushes against this coma, creating the comet's characteristic tail, or more accurately, two tails pointing away from the Sun. The ion tail, consisting of ionized gas molecules, appears bluish and follows the direction of the solar wind precisely, always pointing directly away from the Sun, regardless of the comet's direction of motion. The dust tail, made of larger particles that respond more slowly to solar radiation pressure, appears white or yellow from reflected sunlight and often curves gently along the comet's orbital path. Because these tails always point away from the Sun rather than trailing behind the comet, a comet approaching the Sun travels nucleus first, but after rounding the Sun and heading back toward the outer solar system, it travels tail first. Each close passage to the Sun costs a comet material as volatiles sublimate and escape into space, meaning comets have finite lifespans measured in dozens to hundreds of perihelion passages depending on their composition and orbital characteristics. Short-period comets, those with orbital periods less than 200 years, originate primarily from the Kuiper Belt and have been perturbed by gravitational interactions with Neptune or other planets into orbits that bring them into the inner solar system regularly. Famous examples include Halley's Comet, with a period of 75 to 76 years, which has been observed and recorded by humans for over 2,000 years, appearing in historical records from ancient China, Babylon, and medieval Europe. Long-period comets, those with orbital periods exceeding 200 years or even millions of years, originate from an even more distant region called the Oort cloud. This theoretical spherical shell of icy objects surrounds the entire solar system at distances from about 2,000 to 100,000 astronomical units from the Sun, or roughly halfway to the nearest star. At such vast distances, individual comets are far beyond the detection capability of even our most powerful telescopes, and the Oort cloud's existence is inferred from the orbits of long-period comets that fall into the inner solar system from seemingly random directions. Unlike the Kuiper Belt, which lies in the same plane as the planet's orbits, the Oort cloud forms a spherical distribution surrounding the Sun on all sides. This shell may contain trillions of icy objects with a total mass estimated as several times Earth's mass, though spread across such an enormous volume that the average spacing between objects measures tens of millions of kilometers. Objects in the Oort cloud move so slowly in their distant orbits that orbital period may reach millions of years, and these bodies barely feel the Sun's gravitational pull, making them vulnerable to perturbations from passing stars, massive molecular clouds, and even the gravitational tide from the Milky Way galaxy itself. These external gravitational influences occasionally nudge an Oort cloud object onto a new trajectory that carries it toward the inner solar system, appearing as a long-period comet that may be visiting the inner solar system for the first time in its 4.6 billion-year existence. Some of these comets follow such elongated elliptical orbits that they take millions of years to return to the inner solar system, while others receive gravitational assists from Jupiter or other planets that either eject them from the solar system entirely, sending them into interstellar space, or capture them into shorter period orbits where they'll return in decades or centuries rather than eons. The Oort cloud represents the effective boundary of the Sun's gravitational dominance, defining the edge of what we consider our solar system. Beyond this region, the gravitational influence of other stars become comparable to our Sun's, and objects are no longer gravitationally bound to our star. The Oort cloud's formation remains somewhat mysterious, as objects at such enormous distances couldn't have formed there originally, as material in the solar nebula was far too sparse at such distances for accretion to occur. Instead, these objects likely formed in the region of the giant planets, particularly Neptune, and were scattered outward through gravitational interactions during the solar system's early chaotic period. The Sun's influence extends even beyond the Oort cloud through a stream of charged particles called the solar wind, consisting primarily of electrons and protons, but also including heavier ions flowing outward from the Sun's corona at speeds ranging from 300 to over 800 kilometers per second. This solar wind carries with it the Sun's magnetic field, which becomes stretched and twisted by the Sun's rotation into a vast spiral pattern called the Parker spiral, after physicist Eugene Parker, who predicted the solar wind's existence in 1958. The solar wind density and speed vary depending on solar activity, increasing dramatically during solar storms when coronal mass ejections hurl billions of tons of plasma into space. As this continuous outflow of particles streams outward from the sun, it creates a bubble of solar influence called the heliosphere, which shields the solar system from most of the galactic cosmic radiation that fills interstellar space. The boundary where the solar wind finally slows to subsonic speeds as it encounters the interstellar medium is called the termination shock, located at approximately 80 to 100 astronomical units from the sun, depending on direction, as the heliosphere is not perfectly spherical but compressed in the direction of the sun's motion through space and stretched out behind it. The Voyager 1 and Voyager 2 spacecraft, launched in 1977 to explore the outer planets, continued onward after completing their planetary missions and became the first human-made objects to reach and cross the termination shock, with Voyager 1 crossing in December 2004 at 94 astronomical units and Voyager 2 following in August 2007 at 84 astronomical units. Beyond the termination shock lies a region called the heliosphere, where the solar wind continues outward but at subsonic speeds, turbulently mixing with the incoming interstellar medium. Finally, at approximately 120 astronomical units, the solar wind's pressure becomes too weak to hold back the interstellar medium, and the heliopause marks the true boundary between the solar system and interstellar space. Voyager 1 crossed this boundary in August 2012, and Voyager 2 followed in November 2018, becoming humanity's first messengers to leave our solar system and enter the space between stars. Despite crossing the heliopause, both Voyagers remain within the sun's gravitational influence and will for tens of thousands of years as they coast through the Oort cloud region, though they'll never encounter any Oort cloud objects as the spacing between these bodies is so vast that close encounters are statistically impossible. The configuration of our solar system that we observe today, with small rocky planets in the inner region, a gap occupied by the asteroid belt, then giant planets in the outer system, followed by the Kuiper belt, represents a more dynamic history than simple formation from the solar nebula might suggest. Growing evidence supports the idea that the giant planets haven't always occupied their current positions, but instead migrated significantly during the solar system's first several hundred million years. The NICE model, named after the French city where it was developed, proposes that the giant planets initially formed in more compact orbits than they occupy today, possibly with different ordering, and that gravitational interactions between these planets and the remaining planetesimals of the outer solar system caused dramatic orbital changes. According to this model, as the giant planets scattered planetesimals through gravitational encounters, conservation of momentum caused the planets themselves to migrate, with planets that scattered objects inward moving outward in response, and vice versa. These migrations would have been gradual at first, but may have triggered a period of instability as planets moved into orbital resonances with each other, positions where their orbital periods create simple integer ratios. When planets enter such resonances, their mutual gravitational influence amplifies, potentially causing rapid and dramatic orbital changes. The NICE model suggests that Jupiter and Saturn entered a 2-to-1 resonance approximately 600 million years after the solar system's formation, causing a brief period of extreme instability, lasting perhaps 10 million years, during which Saturn, Uranus, and Neptune all moved outward to their current positions, while Jupiter moved slightly inward. This rapid rearrangement would have scattered planetesimals throughout the solar system, sending some into the inner solar system, where they would bombard the terrestrial planets, others outward to form the Kuiper belt, an Oort cloud, and ejecting many objects from the solar system entirely into interstellar space. This event might explain the late heavy bombardment, a period approximately 4 billion years ago, when impact rates on the Moon and other inner solar system bodies appear to have suddenly increased dramatically before declining again. Lunar rock samples returned by Apollo missions show a clustering of impact melt ages around 3.9 billion years ago, suggesting an intense bombardment period that melted and reworked substantial portions of the lunar crust. This bombardment would have also affected Earth, potentially delivering large quantities of water and organic compounds that may have contributed to the emergence of life shortly after the bombardment ended. as the earliest evidence for life on Earth dates to about 3.8 billion years ago. The NICE model also helps explain several puzzling features of the outer solar system, including why the Kuiper Belt appears to have relatively few objects, despite likely containing more material originally, as planetary migration would have scattered most of these objects. It explains Trident's capture by Neptune, as the chaos of Neptune's outward migration and interaction with numerous planetesimals would have created opportunities for gravitational captures that would be unlikely in the current stable configuration. The model also provides a natural mechanism for delivering objects into the Oort cloud, as planetesimals scattered by the giant planets could be thrown to enormous distances while still remaining weakly bound to the sun's gravity. While many details of planetary migration remain uncertain and continue to be refined as new evidence emerges, the general concept that the solar system's architecture resulted from a dynamic evolutionary process rather than simple formation in current positions has become widely accepted. Looking far into the future, we can consider the ultimate fate awaiting our solar system over timescales measured in billions of years. The most dramatic changes will result from the sun's ongoing evolution, as it exhausts the hydrogen fuel in its core. Stars like our sun spend most of their lives, approximately 10 billion years, in a stable phase called the main sequence, where hydrogen fusion in the core produces outward pressure that balances the inward pull of gravity. Our sun is currently about 4.6 billion years old, meaning it has already consumed roughly half its core hydrogen and has approximately 5 billion years remaining in its main sequence phase. As hydrogen fusion continues, helium accumulates in the core as fusion ash, and this helium core gradually grows more massive. Helium, being denser than hydrogen, causes the core to contract under its own weight, and this contraction actually increases the temperature and pressure at the edge of the core, where hydrogen still exists, causing the hydrogen fusion rate to increase. This sounds counterintuitive, as we might expect a star to dim as it depletes its fuel, but instead the sun has been slowly brightening throughout its lifetime and will continue to do so, increasing its luminosity by approximately 10% every billion years. In about 1 billion years, this increased solar luminosity will raise temperatures on Earth enough to accelerate the weathering of rocks, which pulls carbon dioxide from the atmosphere and locks it in carbonate minerals. Eventually, atmospheric carbon dioxide levels will drop below the threshold required for most plants to perform photosynthesis, causing the biosphere to begin collapsing. Rising temperatures will also accelerate ocean evaporation, and as more water vapor enters the atmosphere, the greenhouse effect will strengthen, creating a positive feedback loop. Within approximately 1 to 2 billion years, Earth's oceans will evaporate entirely, and our planet will transform into a hot, sterile world similar to present-day Venus, though life might persist in isolated pockets where conditions remain favorable. In approximately 5 billion years, the sun will have exhausted all hydrogen in its core. With fusion shut down, nothing counteracts gravitational collapse, and the helium core will contract and heat up, while hydrogen fusion continues in a shell surrounding the core. This shell fusion actually produces more energy than core fusion did, causing the sun's outer layers to expand dramatically, transforming our star into a red giant. Over the course of several hundred million years, the sun's radius will expand to approximately 250 times its current size, engulfing Mercury and Venus entirely as its outer layers reach and surpass Earth's current orbit. Whether Earth survives or is consumed remains uncertain, and depends on several factors. As the sun expands, it will lose mass through an enhanced solar wind, causing its gravitational pull to weaken slightly and allowing Earth's orbit to spiral outward. Calculations suggest Earth might migrate outward just enough to avoid being engulfed, though it would come very close, experiencing extreme heating that would vaporize any remaining atmosphere and melt the surface into a magma ocean. During this red giant phase, which will last approximately 100 million years, temperatures in the outer solar system will increase dramatically,
Saturn's Titan and Jupiter's Europa will see their ices melt, potentially creating brief periods of habitability in regions that spent billions of years frozen, though these habitable periods would last only a cosmically brief period before ending as the sun continues evolving. The increased temperatures and solar wind will also sublimate the ices of Kuiper Belt objects and Oort cloud comets, giving these distant bodies temporary comet-like halos, though no one will be around to observe the spectacular sight. Eventually, temperatures and pressures in the sun's contracting helium core will reach 100 million degrees Celsius, hot enough to ignite helium fusion in a process called helium flash. This sudden ignition releases enormous energy, but because the core is in a degenerate state, where quantum mechanical pressure rather than thermal pressure supports it, the core cannot expand to regulate the reaction, and the fusion rate skyrockets within seconds. The helium flash releases as much energy in a few seconds as the entire Milky Way galaxy produces during the same time, though most of this energy goes into finally lifting the degeneracy and expanding the core rather than being radiated into space. After the dramatic helium flash, the sun will settle into a new stable configuration, fusing helium into carbon and oxygen in its core while hydrogen fusion continues in a surrounding shell. This phase, called the horizontal branch, will last approximately 100 million years, during which the sun will be smaller and less luminous than at the peak of its red giant phase, but still much larger and brighter than today. Eventually, the core's helium will be exhausted, leaving a carbon-oxygen core surrounded by shells of helium and hydrogen fusion. The sun will again expand into a red giant, possibly growing even larger than during the first red giant phase, and will begin pulsating, varying in brightness over periods of months to years. Strong stellar winds will blow away the outer layers, carrying off perhaps half the sun's remaining mass into space. These expelled layers will form an expanding shell of glowing gas called the planetary nebula, lit from within by the exposed hot core. Despite the name, planetary nebulae have nothing to do with planets. Early astronomers using primitive telescopes thought their round, disc-like appearance resembled planets, and the name stuck. The remaining core, now composed of carbon and oxygen with no remaining fusion fuel and not massive enough to contract further and ignite carbon fusion, becomes a white dwarf, an incredibly dense object containing about half the sun's original mass compressed into an Earth-sized sphere. A teaspoon of white dwarf material would weigh several tons on Earth. The white dwarf will initially have a surface temperature exceeding 100,000 degrees Celsius. Glowing brilliant blue-white, but with no fusion to replace radiated heat, it will cool gradually over billions of years, fading through white to yellow to red, and eventually becoming a black dwarf, a cold, dark cinder no longer emitting visible light. This cooling process takes an extraordinarily long time, longer than the current age of the universe, so no true black dwarfs exist yet anywhere in the cosmos. The planets that survive the sun's red giant phases, likely including Mars and the outer planets, will orbit this white dwarf in cold, dark trajectories, receiving negligible heat and light. Jupiter and Saturn will remain frozen, their atmospheres perhaps condensing and snowing out onto their interiors. Neptune and Uranus will become dark ice worlds, invisible except by reflected light from the faint white dwarf or distant stars. Over truly immense timescales, measured in trillions of years, even this remnant solar system will gradually disintegrate. Gravitational interactions with passing stars, though rare, will occasionally disturb planetary orbits slightly. Over many such encounters across trillions of years, some planets will gain energy and be ejected into interstellar space, becoming rogue planets wandering the galaxy, while others will lose energy and spiral inward. The white dwarf itself will eventually cool to match the temperature of the cosmic microwave background radiation, the faint afterglow of the Big Bang that pervades all space. At this point, the former sun will be in thermal equilibrium with the universe, a dark, cold sphere that has reached maximum entropy. If we extend our vision even further to timescales of 10 to the 100 years and beyond, numbers so large they defy human intuition, quantum mechanical effects may cause even the matter of the white dwarf to decay through proton decay or quantum tunneling, though these processes remain theoretical and unobserved. The solar system will have long since dispersed, its planets ejected or fallen into the white dwarf,
and even the atoms that once composed our sun, Earth, and everything we've ever known will eventually return to the fundamental particles from which they came. Yet this far distant future also holds elements of hope and continuity. The heavy elements forged in the sun's interior and expelled in its planetary nebula phase will mix with interstellar gas, enriching it with carbon, oxygen, and other elements essential for life. This enriched material will contribute to future generations of stars and planets, and the atoms that once formed our world will be recycled into new worlds orbiting new stars not yet born. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all came from stars that died before our sun was born. And these atoms will continue through countless more stellar generations, perhaps eventually incorporated into worlds where new forms of life will arise and contemplate their own place in the cosmos. Our solar system, despite its eventual fate, represents just one chapter in an ongoing cosmic story that began with the Big Bang 13.8 billion years ago and will continue far into a future we can barely imagine. For now, we exist in a remarkable epoch when our star provides stable warmth, our planet hosts abundant life, and we possess the intelligence and curiosity to understand our cosmic context. We orbit a typical star, in a typical planetary system, in an ordinary galaxy among hundreds of billions of others, yet our perspective remains unique and precious. The facts about our solar system reveal a cosmic environment of extraordinary complexity, where violent collisions and gravitational chaos shape the architecture we observe, where planets range from Mercury's scorched surface to the frigid darkness beyond Neptune, where moons harbor hidden oceans that might host alien life, and where everything ultimately traces back to a collapsing cloud of gas and dust 4.6 billion years ago. Every planet, moon, asteroid, and comet tells part of the story, preserving evidence of events that occurred billions of years before humans existed. The impact craters on the Moon and Mercury record the intense bombardment of the solar system's youth. The geological activity on Europa and Titan hint at dynamic processes continuing today in unlikely places. The composition of asteroids and comets reveal the chemical makeup of the primordial solar nebula. Even Earth itself serves as evidence, its oceans possibly delivered by cometary impacts, its atmosphere shaped by volcanic outgassing and biological activity, and its very existence dependent on occupying the narrow habitable zone where temperatures allow liquid water. Understanding our solar system provides essential context for understanding ourselves, our origins, and our place in the universe. We are not separate from the solar system, but products of it, composed of materials forged in previous generations of stars, living on a planet that formed from the same primordial disk that created the sun, shaped by impacts and gravitational interactions with other solar system bodies. Dependent on the sun's steady energy output and protected by Jupiter's gravitational influence from excessive impacts. The solar system serves as our cosmic laboratory, the one place where we can study planetary processes up close, land spacecraft on other worlds, sample their atmospheres and surfaces, and test our theories about how planets form and evolve. The lessons learned here inform our understanding of the thousands of exoplanetary systems discovered around other stars, helping us identify which distant worlds might harbor conditions suitable for life. As we continue exploring our solar system with increasingly sophisticated spacecraft and instruments, each new discovery raises new questions and reveals unexpected complexity. We've learned that supposedly dead worlds remain geologically active, that oceans exist far from the sun's warmth, and that organic chemistry occurs in environments nothing like Earth, and that the solar system continues evolving in ways we're only beginning to understand. These discoveries remind us that despite centuries of astronomical observation and decades of space exploration, we've only scratched the surface of understanding our cosmic neighborhood. Future missions will land on Europa and drill through its ice to sample the ocean below, return samples from Mars that might contain evidence of ancient life, explore Titan's hydrocarbon seas with submarines, send probes deep into ice giant atmospheres to understand their compositions, and visit dozens of moons, asteroids, and comets to catalog the diversity of bodies in our solar system. Each mission will answer some questions while raising new ones, continuing the process of discovery that began when our ancestors first looked up at the night sky and wondered about those wandering points of light. The facts about our solar system ground us in physical reality while simultaneously inspiring wonder and curiosity. They remind us that we live in a universe governed by comprehensible physical laws, where matter and energy interact in predictable ways, where nothing is truly static or permanent, and where change occurs on timescales ranging from seconds to billions of years. The solar system story is far from over, continuing to unfold across deep time in ways both predictable and surprising. And our privilege is to exist during this brief epoch when we can observe, explore, and attempt to understand the magnificent cosmic environment that gave us birth and sustains our existence. From the sun's fusion-powered heart to the distant icy bodies of the Oort cloud, from the scorching day side of Mercury to the frozen nitrogen plains of Pluto, from Jupiter's centuries-old storms to the methane rain falling on Titan, our solar system encompasses extraordinary diversity within a relatively small region of space, approximately 1 light-year across, including the Oort cloud, a tiny fraction of the distance to the nearest star. This compact cosmic neighborhood has witnessed 4.6 billion years of evolution, from its violent formation through countless impacts and migration to its current relative stability, and will continue evolving for billions of years more until our sun's eventual death transforms everything once again. As we conclude this journey through our solar system, we recognize that these facts and figures, remarkable as they are, represent more than mere data points to be memorized. They tell a story of origins and evolution, of chaos and order emerging from it, of constant change occurring on timescales both rapid and geological, of unexpected beauty in unexpected places, and of the physical processes that govern not just our solar system but all cosmic structures everywhere. The solar nebula that collapsed 4.6 billion years ago contained within it the potential for everything that followed: the formation of our life-giving sun, the accretion of planets from dust to gas giants, the delivery of water to Earth, the emergence of life and eventually intelligence, and the capacity for that intelligence to understand its own origins. We stand as the solar system examining itself, stardust contemplating stars, matter organized in such a way as to comprehend the physical laws governing matter. This perspective, humbling and empowering simultaneously, represents perhaps the most profound fact of all about our solar system. It created conditions where not only could life emerge, but where that life could evolve the capacity to understand the very processes that created it. To send spacecraft across billions of kilometers to explore distant worlds, to decode the history written in rocks and ice, and to project forward billions of years to envision our solar system's ultimate fate. The accumulation of knowledge about our solar system across centuries of observation and decades of space exploration reveals the power of the scientific method and human curiosity working together. Every fact discussed represents discoveries made by thousands of scientists, engineers, and explorers working across generations, each building on previous knowledge, refining theories, developing new technologies, and gradually constructing an ever more detailed picture of our cosmic neighborhood. From Galileo's first telescopic observations of Jupiter's moons to the Voyager spacecraft crossing into interstellar space, from the Apollo astronauts walking on the moon to rovers exploring Mars' ancient lake beds, humanity has transformed its understanding of the solar system from mythological stories to quantitative scientific knowledge. Yet with all we've learned, mysteries remain, questions still outnumber answers, and the next generation of explorers will undoubtedly discover phenomena we haven't yet imagined. Perhaps they'll find life in Europa's ocean or in the subsurface aquifers of Mars. Perhaps they'll witness a major impact on Jupiter or detect seismic activity on Venus. Perhaps they'll discover new moons around the ice giants or observe the birth of a comet in the Oort cloud. Whatever they discover will add new chapters to the continuing story of our solar system, deepening our understanding while likely raising new questions that will motivate the following generation of explorers. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.